So I'm member of the FAPESP Center for Neuromathematics, which is a new institute. It started last August, granted by FAPESP, and we have several members of the team. Guillermo, Siddhartha, Claudia, Roque, and many others, my students. Okay, so this is the title of a paper I wrote with Eva Locherbar. So how should I... Okay, so a paper I worked with Eva Locherbar, who is also a member of the team. It appeared last year. And I'd like to speak about the model, which I think is an interesting model, but also to give the framework which is behind. And so this is the lesson part of the talk. Okay, so motivation. So, of course, this is Friday. Everybody have been talking about this, but I mean, so a neuron talks to each other by firing sequence of action potentials. We call this a spike. And so you know all this, everybody spoke about this these days. And this is a nice picture of a raster plot. And now this is new. So what kind of questions a mathematician would ask? So how is information external stimulus encoded in these patterns? 2-3 weeks ago, Marcelo Magnasco was here, and I guess he presented a paper he wrote with Tai Fumier about two different types of stimuli and the code they produce. How to model brain plasticity. And well, and then all this phenomenology people have found, and here now I would put how to explain the existence of auto-sustained activity, self-sustained activity, SSA. I remember it was double something, self-sustained activity. So SSA. And at the end, if you are not dead, I would speak half an hour about this, because I have results on this. So now the model. I have a very, very, very big system, and this number is not finite. This is infinity. Finite is 10, 20. 1,000 is no longer finite for any practical means. And 10 to the power 11, it's a countable infinite set. And the idea is to make a model, in which t is time, I is a neuron, and I just indicate if the neuron I has a spike in a time t. Well, time t, I'm considering windows of 3 milliseconds. And I will tell you if there is a spike of this neuron in this window. Okay? Now, background. Our model is very much inspired by integrate and fire models, leak, integrate and fire models. We are encoding these models just by telling what are the times in which a spike occurs. So this is something everybody present to you these last days. Now, this is a new word. The new word is variable length memory. Why variable length memory? Because the membrane potential starts accumulating values after the last time it has a spike. So how many steps you must go back in the past to say something about the probability of having a spike at the next time step? Well, you must go back until you find your last spike. This could be 1 step back, 2 steps back, 3 steps back. And this is a very interesting, well, this is an example of very interesting class of models called the stochastic chains with memory of variable lengths. But now, the new thing is that you don't have just one. We have an entire system of chains of this type. Actually, when I started working with this, with Eva, we have been very much inspired by a paper by Bruno Cessac. Bruno Cessac is a young fellow. He comes from statistical physics. And he wrote a paper in which essentially this is what he does, but he only considered a finite number of neurons. And we can do better than this. Okay, so the model. We have a chain. T is time. This is an infinite vector of zeros and ones. I is a set of all neurons. So T is discrete time. I is countable, and we will consider the case in which I is countable infinite. Time evolution. So, complicated formula. Be prepared, but not that hard. So, at each time step, given the past, neurons update independently from each other. And that means essentially that we are not considering electrical synapses, while only considering chemical synapses. And this is not a big matter. At the end of the talk, I will consider a situation in which we have a chemical synapse. Why not? Because at chemical synapse, the independence, given the past, is no longer true. And so, the probability for each neuron to have a spike or not, this could be 0 or 1, will be a product. So, be careful. This does not mean they are independent, given the past. Given the past. And this is the past. So, I will go back immediately to something much more easy to present. So that's the motivation. And that's the way we present the. So this is typical of an integrator and fire model. So you see, the probability of having a spike at time t at neuron I, given the past, it's a function. The function could depend on I. It's a function of what? Well, you see, here you have two components. This component defines the membrane potential. I am adding above all the other neurons. This is a real number. It could be positive or negative or 0. And then for every neuron J, I'm counting. So forget this, maybe put this equal 1. I'm counting how many spikes they had since the last spike time of I, before t. So this is just the accumulation of charges received by other neurons. And this is the leak effect. This is a function which decreases when time increases. So this is nothing else. This is the integrated, leak integrated and fire model in a very general framework. And this is some kind of aging effect. Actually, I forget this, but you can add this. So Wji is the synaptic weight of neuron J on I. Li of t is the last spike time strictly before time t. And J is a leaky effect, not aging, a leaky effect. Okay? So I want to tell you about this model. With this model, I can tell you rigorous things about self-sustained activity. But now, if I go directly to this model, this is not a lesson, this is a conference. So I need to give you some background information. Okay. Here I have my graph of influence. These are all the neurons which affect I. So when W is different from 0, this means that j affects I. So this is a neighborhood in the graph of interaction of I. He would say that this is like Erdos-Scheni, slightly above criticality. Is this true? I don't know. But I like it because I know how to prove things in this case. So very good, very good. Well done. So if this number is positive or negative, you have excitation. So all this is just integrated and leak integrated and fire models. Now some advertising. This is a new class of non-Markovian process having a countable number of interacting components. I don't know what this. This is from the. Why is these two lines? I don't have these lines. Okay. So here is a first word you don't know, maybe, the word Markov. So I must explain to you what is a Markov process. The other is a countable number of interacting components. And then I continue by saying you, well, it extends a non-trivial way Spitzer's interacting particle systems which are Markovian. So now what is this? In the 70s, a man named Frank Spitzer invented a new domain of probability. He wrote a paper named Interacting Markov Chains. In this paper, there was no proof at all, only conjectures. And 20 persons, 30 persons start to work on this, and this created an entirely new domain in mathematics. There was something before Spitzer. In statistical physics, Metropolis and Glauber in the 50s presented the processes which are of this type to simulate what now we call Markov Monte Carlo. But what Spitzer said was to present an entire group of systems. So typically, you have a countable set of random walks in the lattice, d-dimensional lattice. And they evolve freely, independently, with one exception. They cannot jump one or in a place in which there is already a particle. So he called it a simple exclusion process, because the only interaction was this prohibition to jump to a place where there is something already. And then another model was the voter model. The voter model, I remember first time I met Joe Lebowitz. Joe Lebowitz is our father. And I was a young researcher, and he asked me, please tell me what you are doing. I said, I'm working with the voter model. I said, what? Voter? Voter? What do you mean? Voter model? Voter model? I said, please write it to me. And I said, the voter model. He said, no, the voter model. Because for his voter was water. That was the distinction. So, in the voter model, we are all here who have opinions, A or B, PSDB, PT. So you believe 0, I believe 1, say, and we try to influence each other. So from time to time, I have a clock. The clock rings, and then I choose one of my neighbors, and I look at him, and I take his opinion. So what do you think? Ah, you think 1, so I take 1. If you think the same, I don't change. So questions. How many invariant situations you have for this process? So this is a very deep question. So he invented a group of problems, and this modified in a deep way probability theory. In Brazil, we have a very important group work on this. Very important group. But our model is not a Markovian. Well, we don't know what's Markovian, I must tell you. But you see, in all my description, I only consider the configuration at a given time. I did not need to look back in the past. The present tells me everything I need to know to decide next step. That's Markov. Okay, but our model is not Markov because the brain is not Markovian. Fortunately or unfortunately. It also extends resonance stochastic chains with the memory of variable lengths. Well, Rissanen is a kind of a guru. It was a guru for me for a long time. Rissanen is an incredible person. Rissanen is someone who was very famous because he invented the arithmetic compressor. Rissanen never worked in the university. He worked at IBM, I guess. That's correct, or AT&T? AT&T. So he spent his life thinking about the data compression. And data compression means you want to encode a string of symbols which are received in such a way that the symbols which appear not very often have a small code, and symbols, long code, and symbols which appear very often have a small code. But attention, to appear very often or not depends on the past symbols which appeared. So we must decide, given the past, what is most likely to occur in the next step. So he had this wonderful idea that in many interesting situations, linguistic situations, biological situations like DNA, you don't need to go back very long in the past. You must go back until you find some kind of flag which tells you, here you have enough information to decide about the next step. So this is clear when you do agreement of writing a text. So you must stay in the noun, in the phrase. And so he had this idea that to decide, to predict next symbol, you must go back in the past, but the number of steps is a function of the past itself. Well, why is this so important? Because if you want to predict things, you need to make statistics. And if you all the time you need to make, say, 10 steps back in the past, even with just two symbols, 2 to the power 10 is a lot, is 1,000. And this makes impossible to make statistics if you impose a fixed amount of steps back in the past. Nevertheless, life requires very often that you consider more than the last step or the present situation. Ask Brazilian, we all know about what happened in Maracanã 64 years ago. We all know, in 64 years ago, at the final of the World Cup, Brazil was defeated by Uruguay. And now, we will remember what happened this year. Forever. This is long memory. People who work in the stock market, they remember 29. Because, well, and if you look at the longest time series in the history, which is the measure of the flow of the Rio Nilo, River Nile. So it started a very long time ago, so in the Bible. 7 years of prosperity and 7 years of... So if you look at this, you see statistically that the memory of this time series has a very heavy tail. But then it's important what this man saw. This is a paper he wrote in '83. He said, well, we need to go back to the past in most situations. This is a wonderful model for reality. A number of steps which is a function of the past itself. Well, this is something which happened to us, into our model, but in our model, only locally. So we generalize both. And so I will be obliged to speak about, tell you what is Markov, what is variable length. Well, and what we are going to build is a chain of infinite order. So we must, for the entire chain, go back to the infinite past in a non-countable state space. This is a non-trivial model. It's a very interesting model for trees. Trees like very much. It's tree in the name of the okay. And so now the question is why so in the movie by Jean-Luc Godard about Carmen, there is a point in which Don José, you know, in Carmen there is a soldier and Carmen. And the soldier falls in love by this wonderful woman, which was a very good idea and a very bad idea at the same time. So he was dispirited. And at a certain point he asks in French, pourquoi faut-il que les femmes existent? So, translate to me. Why should women exist? So you could ask, why should mathematicians exist? Well, most of the time, there is an old discussion with physicists. Old discussion. So I've been working in statistical physics my entire life. I also was editor of Journal of Statistical Physics. So most of the time, people, very bright people like Guillermo Cecchi, Hockey, no, it's unfair with Guillermo. But Derrida, Giorgio Parisi, say, well, what are you going to do? You prove the theorem telling us that this occurs, but we knew it already. We knew because experimentally. So the only way to convince as physicists that mathematics is unavoidable is when we show physicists that the conjecture he made is wrong. I try to do it with Rocket's end. The only way to keep the audience for 2 hours is to make all the time this kind of small joke. Otherwise, Okay, my friends. Now, what are the keywords I have been using until now? Keywords: Markov chains, stochastic chains with memory of variable length, and systems with a countable number of interacting components. Okay, so attention, next step is for you, Siddhartha. I'm going to speak about a paper you wrote in 2007 with several people, not well known, Miguel something, I don't remember the name. So reasoning introduces these chains. No, so this lesson starts. In a moment I will go to the blackboard and do things, but let me. So reasoning introduces these models not for probabilistic reasons, just because you want to make a data compression. The name of the paper is a wonderful paper, 7 pages paper, very short, very bright. The title of the paper is A Universal System for Data Compression. And he called this model a finitely generated source or a tree machine. Tree because the way you organize the past you need is like a tree. And then this paper became very and totally unknown by probabilists and physicists. In 1990, these two fellows, Bühlmann and Weiner, wrote a paper in which they did again the same Risson did in a much lengthy way, filling all the details Risson did not feel necessary to fill. But they did, and then probabilists and statisticians become aware. They call it variable length Markov chain, which is a very bad name. I don't tell you why it's a bad name. Mas for você? Amém. And the people in bioinformatics also call it prediction suffix tree. Okay, so I think I'll go. So our system takes its value. So you have I is countable. So countable means you can enumerate it. The first one, the second one, the third one, and so on. So that is the definition of countable. And then you have x of t, which depends on I. For every I, you can read me. People back can read me. Why you are so far away from me? You have lots of places here. Why you are so far away? Strange. So you take I here, and then this is either 0 or 1. And so this means that x of t belongs to the set 0, 1 to the power I. So this means all the sequences, so say I is, so this means all the sequences indexed by I. So you could have 0, 0, 0, 0, 0, could have 1, 0, 0, 0, 0. So my set is 0, 1 to the power I. This is a notation to represent the set of all sequences indexed by I. So I is 1, 2, 3, 4, 5, and having values either 0 or 1. And then, at the end of the 19th century, a man named Cantor started discussing this kind of different types of infinity. Cantor realized that among the sets which are not finite, you can have different types of infinity. You can have countable things. What is a countable thing? Well, you can say the first one, the second one, the third one. But then you can have things like this huge set, and this is not countable. And so, thank you to Guilherme, I will tell you how Cantor proved that this is not countable. So let's suppose someone say, no, you are wrong. This set is countable. I make a list with all. So the first one, okay, show me your list. That's my list. So this is the first. That's the second. That's the third, and so on. Of course, it's a very long list. But trust me, I spent my entire day yesterday making it complete. I said, no, your list is not complete. How do you know? You did not read the entire list. No, your list cannot be complete. Prove me. I'm a mathematician, I can do it. So let's assume your list is complete. Okay. Now I give you, Claudia, a sequence which is not in the list. So, wow, how can you tell me this? I assure you, don't you trust me? Well, I will give you an element, a sequence, which is not in the list. I do the following. My first element is the opposite of the first element which is here. This is 0, so it's 1. My second element is the opposite of the second element of the list. This is 0, so it will be 1 also. My third element will be, and so on. So this is 1, I have 0. So this sequence is not in the set, because it differs at least one symbol for any element. So this set is not countable. This is a set which has the cardinality is C. So that's all the question. Thank you. So of course Guillermo knows it. So this set is not countable. You cannot make a list. So but that's a situation, a configuration of spiking activity in the brain. Well, it's finite, yes, but not really. It's not countable. It's another category. So, okay, now let me tell you something. Then I'll get back to. So if you have questions, please ask me. Today at 6 o'clock, I guess, 6 o'clock, 6 p.m., 6 p.m., 6 p.m., 6:15. Aldana will give you an exercise class. We have a sequence of exercise. I guess she distributed. So you have your okay, now I'm going to tell you what is a Markov process. So this is very elementary, but usually people in biology don't have, or in computer science, they don't learn. Yeah? Okay, Markov chains. So Markov is a Russian mathematician. He invented this chain 101 years ago. He wanted to make a model for the sequence of consonants and vowels, so two symbols, C and V, in the poem Yevgen Onegin by the Russian poet Pushkin. So he realized that the consonants and vowels are not put independently, because that's not the way a language is structured. So he thinks, what is the simplest way to introduce dependence from the past? So the next symbol is random. It depends of the past. So he said, well, the simplest way to do it, so let me call my sequence x0, x1, x2, and now xn belongs to an alphabet A, and I take this finite or countable. Let's take it finite. So the simplest way to produce a dependent sequence is the following. I say, for any index n, I can generate xn with an algorithm of the type, it's a function of the last symbol, and here I put a uniform random variable. And I must tell you how to start. So let's suppose that x minus n start with a fixed symbol. And for all n greater or equal 0, do this. So f is a function which goes from a times 0, 1 to a. So let me give you an example. So if you can generate your chain like this, you call this chain a Markov chain. In the case of the poem Yevgeny Onegin, to decide if the next step is a consonant or a vowel, you just have to look back one step to see what to decide. Of course, it's not a good model for language, but, well, it was the simplest idea one could have. Now, an example of this is the following. Can you read here in the back? No, you can't. You can? Okay. So let's suppose I have just two symbols. A is here equals 0, 1. And then I took my f in the following way. F of A and U is indicator of U being smaller than a certain R of A. So U is a number between 0 and 1. And R of 0 is a parameter, and R of 1 is a parameter. And in the afternoon, Aldana will show you several examples. So I will start a simulation. So this is a school. I will do a simulation immediately. It's a simpler simulation than the one Rodrigo did yesterday. Much simpler. So let's suppose I take r of 0 equal, I don't know, 0.7, and r of 1, I don't know, 0.2. They are not related. They're in the, I choose the way I want. And then I take x0, x minus 1 equal 1. And then I must generate the uniform random variable. So please tell me the last 2 digits of your cell phone. 4? Yours? 5, 3. Okay, so here I have three uniform random variables. I just choose it with my computer. Now I start with x minus 1 equals 0. I must define what is x0. Or it's a function of x minus 1, which is 1, and of u of 0. And this is 1 if the following condition is satisfied. You see, r of a. So r of 1. R of 1 is 0.2. Is 1, u0 is 0.48. So people back in the room, is it true that 0.48 is smaller than 0.2? No, it's not. So this is 0. Okay, next symbol is 0. And so on. Okay? Okay, so this is the definition of Markov chain from an algorithmic point of view. But now you say, well, to describe the language, one step back does not seem to be enough. One step back. So maybe it's better to use 2 steps back, or maybe even 3 steps back. Okay, no problem. It's very easy to modify the definition and here I could say, well, this is original definition. Okay, I'd say, okay, xn, now it's a function of xn minus 1, xn minus 2. Or maybe 3 steps back is better. Well, since I'm a mathematician, I prefer to do it in a general way. So k steps. I go back up to xn minus k u of n. I can do it. And then the first step, I must tell you how to choose. Okay, I choose my first step. So instead of doing this, now I do this, which is more general. So fix the k, choose x minus k, x minus 1 in a certain way, choose, and then for n greater or equal 0, do this. So now you have a function which look back k steps, choose a uniform random variable, the last 2 numbers of Guillermo's cell phone, and then I define the next step, and so on. Mathematically, this is the same object. Instead of it looking just a symbol, I look strings of k symbols. So this means that I'm considering order 1 in a bigger alphabet, which is a to the power k. Now, this is what people call order k Markov chain with memory of length k. K. By the way, I could consider also the case k equals 0. In this case, x to n is just a function of u of n. And this is the case of independent random variables. Okay, now you know what is a Markov chain of order, of memory. Que horas são? Que horas tienes? 11:25. Okay. No, but because I want to break. Okay, now, what is the problem with this definition? This is a wonderful definition. It's very easy model. It's very easy to simulate, and you will have a very nice mathematical theory of it. In particular, we can prove that for good models, in any way you start, the distribution of the chain converges to a fixed probability number, which does not depend on the initial symbols. So this is a remarkable theory which was developed in the 50s. So you can prove that you can start in any way if f is reasonable. You converge it to a distribution which does not depend on the starting point. Okay? Now, what is the problem with this sequence, with this theory? That we need, even for a equals 0, 1, we need to define r, a minus k, a minus 1 for all these symbols. And now this is too big. The number of parameters you need to introduce is too big. It increases in an exponential way. This is the curse of dimension. You cannot work with Markov chains of order 10. You can't. You don't have enough data to estimate. And order 10 is not that long. Remember, everybody knows what happened in Brazil 64 years ago in Maracanã in July. We even know who made the second Uruguayan goal. Was? Exactly. So we remember everything. So what to do? Yeah, but we remember this is something which is part of our history. So the good news is the following. In real data, when you consider real biological data, you don't need to look back a fixed number of steps. It depends on the situation. And I can exemplify to you immediately. I will take this text. I never saw it before. Okay. So I will show you the way we work. So of course, everybody now is going to use the fact that they know English. So it's a little bit unfair. But this game was invented in the 50s by Shannon himself. By the way, reasoning got the Shannon Medal 3 years ago. Okay, so now I will do the game with you to show you that this k in general change. So you can have here a k which changes as a function of the past. Okay. Since I spoke a lot about your paper yesterday, but you are not here to help me, I was saying, well, Bags and Plant said that, where is Bags? So, okay, now here I have a text. We don't know this text. It's an English text. I ask you to tell me, I'm taking a sentence by chance. I ask you to tell me what is the first letter of the sentence. T. So you said T, but it's not T, it's F. Now tell me what is the second letter. Oh, very good. And how do you know? Because you take into account Now tell me what is the third? Ah, very good. And now the next one. Well, now you know that's the empty place. And now, so you have seen, in order to identify O, he used the F. In order to identify with probability almost 1, he knew F and O. Now, try again. And this is very tough because information is stopped somehow. Tell us. T. Well, he likes very much T. But it's not T, it's I. And now? So it's not fair because he's trying to think in a text like this what kind of sentence to use. So he can guess in a correct way. You see, the third symbol will be immediate. Now he hesitates. He likes T. No, it's N. It's N. Huh? Which one now? No, it's not F. It's S. And you see the way we work to guess the next. We use information, but you must look back in the past. A number of steps, it depends. For instance, here, you use this information. Because, for instance, it's something which is frozen, everybody uses. For instance, okay, so reasoning make this observation a useful thing. He said, when you look at DNA data, you have points in which you say, here I stop encoding. When you look at proteins, the same thing. And so the idea is the following. The model he considers, and this is a wonderful model, you should use it because it's so flexible and so powerful and so economic. It's a shame probabilists and statisticians and neurobiologists don't know about these things. So let's make an effort to, this is the one. So here, you see here, instead of taking a fixed K, Siddhartha, pay attention because it will be your turn in a very few minutes. I will speak about your paper. Here you put an L, which is a function of the past itself. So, and this function is what the probabilists call, well, there is a measurability condition. To be useful, so now I'm here, I want to guess the symbol here. So I go back one step back in the past, and I want to use past information to deduce the next. So I look and say, no, this is not enough. Like for you in the end, it was not clear. I alone. Yeah? But well, for in, it become more, so Claudia says, instantly. So I go back one other step and say, well, this and this, well, I still don't know, I'm not sure. Then I say, aha, with these 3 steps, I know everything. So the decision I make must depend only on the number of steps I did until there. I cannot tell, well, go back to the future and then if you see, no. So this L is measurable with respect to, so this is a technical thing, but you understand. It's a kind of information you must give to someone to find a way. It's terrible when someone say, you go until the bridge. When you are at the bridge, it's too late. You must go back. So L must tell you when you need to stop. Just take into account what you have seen until now. So, and this was the object of reasoning introduced. So now I guess I can get back there. And I will stop when I start attacking the paper by Siddhartha. Okay, when you have, so advertising. a syntactic structure, a DNA sequence, a protein, a raster plot. It's natural to assume that each symbol depends only on a finite suffix. Suffix means the concluding part of the sequence, whose length depends on the path. So that's the wonderful idea this man had 31 years ago. Be careful, we are not making the usual Markovian assumption. At each step, we are under the influence of a suffix of the past whose length depends on the past itself. We saw it. Well, in general, we hope that this length is finite. We don't need to go back. But it's not bounded in general. So I cannot tell you, look, you go back to the past, but you don't need to go back more than 10 steps. You don't know. So what we really have is a chain of infinite order. But what is wonderful is that if I ask a mathematician, give me an example of a chain of infinite order, that's tough. So he'll tell me about a dynamical system, a hyperbolic, but this is elementary. I can give this example for kids in kindergarten. Okay, now some terminology. Calls the relevant suffix of the past a context. So I will speak about context all the time. The set of all contexts should have the suffix property. This means that no context is a suffix of another, is a proper suffix. Otherwise, the information would be useless. No context is a proper suffix of the context. And this means that you can identify the end of each context without knowing what happened sooner. As the suffix properties implies that the set of all contexts can be represented as a rooted tree. Context-free grammars are a branching process. No, this is not kind of tree. These trees are more related to the classification trees by Bryman, but nothing to do with the content. Very good point. So, this is just a coincidence. Recently was not aware of Chomsky's hierarchy of formal grammars. No, I don't think he knew about it. Let me tell you something. So, Risson is a quite a person, difficult, very nice person, very difficult. And he likes very much, he's a very famous man. He invented the MDL approach in statistics, minimum description. So he's a very famous statistician. And then someone asked him when he was 75 years old, Professor Risson, tell us what was the most difficult thing for you to do in your life? He said, well, I think the most big difficulty I had was when I started learning statistics. So, oh my, how come? Professor, you are a famous statistician. And in your young days, you worked in things like algebraic topology. How can you say that statistics was the most difficult thing you had in your life to learn? He said, well, because it's very hard to learn something which is meaningless. And he likes very much to start his talks for a statistician by saying how he considers statistician ignorant people doing black magic and things like this. So, very nice person. I'm not a statistician. So, the model is the following. You are in the Second World War. You are in the resistance in France. You are sending messages to English submarine to sell. So you must take care. So you have the following thing. You have here a lamp. And you do some Morse code, pa, 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 pa. Well, but then you have a device. And the device you can represent like a window, which can be opened or closed, and in an independent way. And then here you have an observer. Well, if the light is shining and the window is open, the light goes and can be perceived by the man observing. Now, let me call xn is the state of the light at the end step. It could be either 1 or 0. 1 if the light is on. And let me call Cn the state of the window at time n. And this could be 1 or 0, and 1 if it is open. But what you perceive here is a combination of both. Let me call y of n what you see. Y of n is what you see. So you see light if there is light and the window is open. So yn is xn multiplied by c of n. Now let me put some temporal structure here. Let's suppose xn is a Markov chain with memory of length, length 1. So the simplest case. Okay? Now the question is, what is y of n? Is y of n a Markov chain of length of order 1, of order 2, of order 3, of order what? So this question you should be able to answer now. And the answer is surprising. And it has to do directly with a result by Siddhartha. I'm going to quote you, Siddhartha, in a few minutes. So, you see, y of n is a very surprising chain. You know what is the length of the memory of the sequence y of n? Independent, yes. Yes, good point. These are independent. So the state of the window is independent of, and these are IID, independent. So it's independent of the chain, and the device is open or closed in a totally random way. So let's say that probability of xn to be equal 1 is, said, I don't know, epsilon, but it's independent. So you have a Markov chain which is observed through a device. The device is dependent on the Markov chain, and it can be either open or closed in an independent way, and this decision is taken. It could be Markov also, but the simplest case. Okay, it's clear the problem. I can erase above. I will erase here. I will erase here this wonderful picture. So let me draw here this chain of what I really see. So let's suppose that's the chain y of n. I wanted to predict y of n. And then I go back in the past, and here I see 0. And here I see 0. And here I see 0. And maybe here I see 1. Well, when I have 0, I don't know what's going on. Because 0 could be no light, or the light is on, but the window is closed. So I must go back until I see 1. Because here I know that the light was on and the window was on. Here I don't know. Now, in order to predict, and this is one of the exercises, it's very easy to make the computations. But now you see, I must go back in the past until I see for the first time the symbol 1, and then I can compute everything. It's elementary, a little bit boring computation, but no big deal. So, in this case, what are the portions of the past I need to consider? I need to consider in order to predict next symbol. So the probability of xn of yn being, say, equal 1, given the past, the portion of the past I must consider is until I find for the first time the symbol 1. What occurs before, it's useless. All the information I need is here, because this is a Markov chain. If I know that here xn minus L is 1, I don't need to go back in the past. So the collection of passes I need to consider is the set of all strings of all suffixes, which go until I find for the first time the symbol 1. And this is either the last symbol was 1, or maybe it was 0 and then this was 1, or maybe it was 0, 0 and then it was 1. In general, 0, 0, 0, 0, 1. So if I set it right as tau, this set here, of course I have a degenerated case in the end, at the end. So I hope to be able to prove that this has probability 0. So, and this is a tree. This is a tree with a root and with labels to say who is what. So what is a tree I'm representing here? This tree which looks like a comb. So this way is 1, this direction is 0. So the leaves of the tree is 1. Here is 1, 0, so 0. Here is 1, 0, 0. This is 0, 0. This is 1, 0, 0, 0. And so on to the power k. So this is a tree of contexts corresponding to this situation. So it's clear why it's a tree. It's clear that no leaf, no context is a suffix of all other contexts. And you have also, and this is a very nice model. This model says you that every time you find the symbol 1, you forget the past. This is called a renewal process. Okay, now last 2 minutes and I stop. I will go very fast until Siddhartha. And then I stop and continue later. Okay, that's the example. So you see, that's the example. I have an alphabet with 0, 1. That's my set of contexts. To define the problem, I must tell you what's the probability of having a symbol 1 given this. So here I invert to make it simpler. So you have a countable set of parameters. Okay, this is a mathematical subtlety. Now the question we have been waiting all this time. Can you find samples produced by renewal chains when we observe experimental spike trains? Because of course, 0, 1, I'm thinking about having a spike or not. So I'm telling you about a process which are produced by a lamp, a window, someone observing. In this sequence, every time I find the symbol 1, I forget the past. It's a renewal process. That does not seem to be very realistic from the, what do you think, John? No, not very realistic. Yes, I don't think we can find it. Can we find a sample? What do you think? Let's vote. What do you think, Daniel? Can we find Yes, okay. Good answer. But he knew already. Surprise! So when you look at the data, Siddhartha and co-authors investigated in a paper which we have been using a lot. So we found that 25% of the neurons of the hippocampus behave like a renewal process. And now, well, could say, well, you are kidding. How do you know? Oh, that's a paper. The question, how do you know? How do you know this? And the answer is, we did the statistical model selection. And the procedure of model selection selects the renewal process as the process which is the best. Best in two senses. It must fulfill two opposite conditions. It must fit well the data. So the data, the sample, should have the greatest possible likelihood if you consider that this was a model. But also it must be economic. So you must have this balance between economy, because otherwise I start modeling the noise. So that was the principle recently introduced, MDL, minimum description length. He said, look, you want to compress data. When you compress data without losing information, like when you do zip, so zip, you zip your data. The file, the compressed file has two parts. A starting part in which you describe, for the one who receives your compressed file, you describe your compressor in such a way that he can decompress the data. And then you have the compressed file. So it's useless to have a compressed file very short, but with an introduction very long. So you must minimize both. So that's the eternal situation in statistics and in data compression. Modeling means having a class of models which are not too big, not too expensive, and fitting well the data. Well, it turns out that for 25% of the neurons of the hippocampus, of the data observed by Siddhartha and co-authors, the best model was, and we know it because we did the statistical model selection. And now, last sentence before starting for 10 minutes, I lost. Okay, so I'm going to do water. And then I spent 50 minutes playing what we did, and then for my model, okay? Okay. So my last question was, what is statistical model selection? And then Rodrigo asked me, did you make a cross-validation? Okay. So I explained you how to make statistical model selection for a simpler case, for Markov chains of fixed order. And you understand why it's simpler, and then I tell you the good news that you can do it for trees also. Now, let us suppose that I have a sample so this was choosing at random. This is a spike train or a raster plot or whatever. It's given. And then, since I'm a very powerful, what's the name of the character? Ent. So I know by superior instructions, God tells me, look, this data was produced by a stochastic chain. It was produced by a stochastic chain with memory given by tau, encoded by tau, given by the 3 tau. So tau, now tau, I will take tau finite. Okay, let's suppose I'm still in 0, 1, and well, I know that this is the tree I have. Okay, I know it. But I don't know the probability associated to the context. But because the interesting thing is that when I am in this context, I know that this information is all I need to predict next symbol. If my last symbol was was 0, and then I have another 0, I arrive here, and this is all I need. So the model is complete when I give you the tree, and associated to each context, I give you a transition probability. But now I know tau, I don't know the family of probability measures indexed by the leaves, by the context. I don't know. So that's the first statistical problem you can. I have the model, but I don't know the parameters. Okay? So it's quite intuitive. So the problem is how to estimate how to infer probability given tau. And this, if you think a little bit, is quite, what we do is called technically is a maximum likelihood estimator. But instead of explaining why it's the maximum likelihood, the intuition is clear. If someone who never had lessons of statistics think about it, you say, well, I have this context. I want to know what is the probability of having 1 after 2 zeros, or of having 0 after 2 zeros. I don't know this. I want to estimate. It's quite clear how we should proceed. We just count how many times we have 0 followed by 1, and how many times we have this followed by 0. So I can, this counting, I write this way. This is the number of times I have seen this sequence in my sample. This is the number of times I have seen this sequence in my sample. And then how to estimate this? So the estimation, I put a hat to indicate this estimation. Intuitively, I see the proportion of times I have seen 0, 0 followed by 1 divided by the number of times I have 0, 0 followed by anything, 0 or 1. And this is exactly the number of times I have seen 0, 0 followed by 1 plus number of times I have seen 0, 0 followed by 0. So this is very intuitive. If I want to estimate the probability of having a symbol 1 after observing 0, 0, this is what intuitively you should do. We just see the proportion of times after visiting 0, 0, we jump to 1. So this is quite clear. And the good news is that by the law of large numbers, this converges. This converges precisely to the probability which was attached to the context. Is that clear? Is that clear? It should be intuitive. Usually we do it in a more, we make a computation to show that this is the values for the probabilities which maximize the likelihood of the sample given that the sample was produced by this tree. This is just Lagrange multipliers computation, but it's intuitive. So this is the way, if I know tau, I can compute the probability associated to each context. Now, this was not Guillermo's Rodrigo's question. Rodrigo's question is, how do I know that the tree was tau? Because that was the important part. That was the striking information. Siddhartha, you must know your sample was produced by renewal process. Shame on you.
Only 25%.
Okay. So you should explain for me. You should explain to me why these 25% are so strange. So that's a good question. I don't know. Yes, a good. Yes, it's a good. Now, I need to identify the tree. That's the real task, and that was what Rissanen did when he started. He said, "Look, I have this model, and I have this way to identify the tree," and he called it the algorithm context, the name of the algorithm. And then he did it for the case of finite trees, and then several people, including myself, generalized it for several cases. But now, trees are complicated objects because they are not in an ordered set. So there is a trick result I'll tell you in a few minutes. I will tell you what to do in the case of Markov chains of fixed order. Well, if instead of having a tree, I have a Markov chain of fixed order, what would be the situation? Sample So I have a sample, and since I'm a very powerful character, I know it was produced by a Markov chain of fixed order. So produced by a Markov chain with memory of length k. But I don't know k. K bar, I don't know. So God forgot telling me this precise detail. What should I do? Okay. If, well, we know already that for k fixed, we can estimate the transition probabilities of having B given that the past symbols. This we estimate just by looking at the proportion of times this sequence. So when I write this, I mean A minus K, A minus 1 is followed by B divided by NN A minus K, followed by Z for any Z in A. So this is the intuitive estimator. We just see all the times the sequence pass by A minus K, A minus 1, what is the proportion of times in which after it jumps to B? Okay. And the good result, the good news is that P and K, B, this converges when the sample size increases to the real value, to the value of the chain which generated the sample. So this is a consistency. This is a consequence of the law of large numbers. It's a complicated law of large numbers because its independence is not clear. The law of large numbers is what tells us that we can do experiments and have stable results. So you can reproduce the experiment several times. You can look at the slices of cortex several times. And you always get to 1.5, hopefully. Okay. Often. So it says that if you reproduce the experiment several times under the same conditions and some kind of independence, the proportion converges. Now, I don't know the value of k bar. I must find it. Now, what is the situation? Situation is the following. Let's suppose, just to fix ideas, that I have a k bar equal, say, 2. If k, it could be just to make people believe it's easier, k bar of 2 is the same. Now, if I compute the value of a minus 1, a minus 2, a minus 3, now, I'm telling you, my sequence xn is a function of xn minus 1, xn minus 2, u of n. This is what is here. To generate my sequence, the last 2 steps in the past are enough. I don't need. Now, here I put extra information. So I'm considering a bigger function in which I tell you also, but this is useless. I'm telling you, it's useless. I'm not using this information. So this, if I compute it, should be equal to PB a minus 1, a minus 2. By assumption, this information is useless. So if the law of large numbers works, it should give us the same result if I put the extra information. So now you start seeing how we can identify. Oh, okay, compute all the transition probabilities, and you know what is the right value of k bar when the extra information you add is no longer, does not change the result. So that's it. But now Rodrigo thinks he's cheating. This man is not telling you the truth. Why? Because this should be true. So the results say, well, you go until for the estimation, the limit of the estimation is equal to the limit of the estimation. But in the limit, we all will be dead, because we only have an amount and a finite amount of time to live. So we cannot consider asymptotic results as... so what should we do? So we must identify when this starts becoming equal. It will never be equal except in the infinite. And then there is a very nice empirical fact, which is also a theorem. And I'll tell you this fact as an experimental fact. It's a very deep result, and I'm sure we could use it for some of the problems we considered yesterday. Well, the history of this fact is not that clear. Probably it was known by people in the 80s, under the influence of Kolmogorov, I'm sure, 70s. People started asking the following type of question. I give you a sample, a sequence of zeros, 1. Tell me if this was produced by a fair coin, yes or not. So it's the idea that you need to extract the information about the structure of the source just by looking at the sequence. And this is the beginning of modern statistical model selection. Okay, in this case, there was a criterion invented in the 80s by a man named Gideon Schwartz. He called the Bayesian information criterion. So probably he had the intuition. The Bayesian information criteria was considered the final result for for 20 years, but actually the real proof, the final proof was given in 1999 by Paul Shields and Imre Cisa in a paper which appears in Annals of Statistics. And if you look at the paper by Cisa, the result is already there, but the hiding, I will tell you the truth. You do the following. So here we know how to estimate the probability transition for any given k. And we know that at some point it should stop because we are adding useless information. Is that clear? Now, let me do the following. So you have the sample. You have the sample. Then I estimate for every k up to a certain point, I estimate the probability. I put a hat here to say that this is estimation. Using transitions of order k, and that's the sample. That's the sample. The sample is fixed. Now, you know, the probability of sample is a product of things. And we hate working with products. It's much better to work with sums. That's why in the 16th century they invented the logarithms to be able to trade enough. So you take here the logarithm of it. And then you call it L of k. So k is the order, is the length of the memory. So the sample is fixed. You consider the logarithm of the likelihood, of the probability of the sample, assuming it was produced by a Markov chain of order k. Now, this is a function which associates to each k a L of k. And now, I give you a news which are impressive, but it's very obvious. This function is increasing. It is strictly increasing. This is strictly increasing. Well, that's very intuitive. When I increase k, I'm increasing my model. I'm giving more details. So it's clear that I can fit better the data. Now, it's increasing by convexity reasons. This is for people who know Jensen's inequality. That's Jensen's inequalities. But it's very intuitive. More details I add to the model, more things I can give you. Now, what is the shape of this increasing function? Now, get prepared, because I tell you something so wonderful. And I found it in a very surprising way. I was working on this problem, but with trees. Of course, k has the fact that you can say 1 is smaller than 2, is smaller than 3. For 3, it's not that clear. But, well, there is some ordering which appears. And I did not know how to do this comparison. And then I realized, I was working with a student of mine, a PhD student, and we saw, I said, look, it's incredible, because it was simulated data. And then something is going on here. That for the tree. So get prepared, because this is wonderful. What we saw was the following. What we saw was that this is a negative value. It's logarithm of something which is between 0 and 1. So here you put L of k, and here you put k. And the shape of L, that's the universal fact, is this one. Get ready? You have an inflection. So here, you have something which increases like n. N is the size of the sample. It's proportional to n. N is the size of the sample size. And here, well, it's even stronger than this. It's almost flat. It keeps increasing because it's still increasing. But here you have a small o of log of n. And now, since that was simulated data, we knew what was the right value. And guess what? Where is the right value? Of course, it should be where it is. That's the right value.
Does real data show the same thing
Yeah,
all the time?
all the time. That's a theorem.
Is
Yeah.
it always that sharp?
Yes. Well, look, my experience is limited. I worked with linguistic data, and it's more general than Markov chain. It works also for context-free models, because what is at stake here is the fact that you must have a chain of embedded models. What's going on is the following: when you have the trees, the bigger the tree, the bigger the number of degrees of freedom. Now, you could try to cut degrees of freedom. If you do it in the right way, using the Bayes information criteria, you get a sequence of champion trees. A champion tree is a champion for a certain number of degrees of freedom. You can rephrase it in a different way. The champion for a certain penalty term. So one way of putting this in the BIC is that you want to have the best possible quality. How much do you want to pay for this quality? Give me your price, I give you the best quality. And this is a penalizing term. What people understand is that you must penalize by something which is much smaller than n and much bigger than logarithm of n. So, in the BIC, the penalty term is multiplied by log of n, which is much smaller than n and much bigger than n. But there is a constant, a penalty constant. And I remember I took my phone and I called David Brillinger. Of course, Brillinger is a god for us because he was the first one to look at spiked trains with Pepe Segundo in the 70s. But he's also my friend. Now I'm avoiding him because he's a fan of football. And I don't want to have discussions with him. I don't want. I'm sure the first thing he will start. Okay. I don't like football. Maybe no, I like it very much. So I asked David and said, David, I have a problem. I have an experimental problem. I want to find a tree for linguistic reasons, and there was a tree I liked very much for some personal reasons. And I realized that I could have this tree if I put a penalty term, a certain penalty term. So I asked him, David, what should I do? He said, very good question, Antonio, very good question. Try to make cross-simulation, cross-validation. Ask linguists about it, they don't know. I cannot ask Siddhartha, do you think it's reasonable to have a renewal process? What can Siddhartha tell me? Yeah, so so I must tell him why I believe it. And then this was a solution, because if you make the penalty term to increase, you have smaller and smaller trees, and they're embedded. So the same picture is true. So that's the final model selection procedure. You choose your estimated order here, or you estimated the tree here. And this is a theorem. Of course, the question is, this is true. The theorem, it says, if your data was generated by a context tree model, then when you look at your champion trees, the right tree will be there, and there will be an inflection at this point. No data was never generated by a context tree model. So no data was never generated by a Markov chain or a Gaussian. So what we're doing, we're making approximations. So maybe my approximation is bad, and then I don't know. But my religion now, Rodrigo, John, is the following. We think we should try to find this in all kind of data. If we can have a sequence of models, try to identify this inflection point. And, well, when you have a new idea, so this appeared in a paper I wrote with other people is called as the smallest maximizer criterion. So if you're interested, I can give you, or go to archive. It appeared in Annals of Applied Statistics last year. And then we realized that Pascal Massard in France had the same idea. He called it the slope heuristics. And he looked at the error term in a regression model. You want to identify the number of steps back in your regressor, and then the error term is stable and then it jumps. So I guess my feeling that you can find it in all kind of problem. It has not to do with the particular structure of the Markov problem. Back to the paper. Okay, no, I won't do this. Okay, so this is an interesting model. Okay, look it. I cannot tell you it in minus 10 minutes. Okay. Okay, no, the only thing I would like to tell you is that, well, when I finished the model, I said, we need to be able to verify some phenomenological fact in the literature. So I found this paper by Goldberg, and he said, in many experimental setups, the empirical correlation between successive interspike intervals is very small. And then Gessner and Kitzler say, indicating that description of a spike in a stationary renewal process is a good approximation. So it was in this Goldberg et al. Model. So he said, maybe our model could fulfill this, but then I needed to introduce the interaction, the reasonable interaction, and the data by the data shows exactly this. It's the same observation. So this is something which appears and appears again. And then, of course, it's more complicated. In this paper, they say that they are negatively correlated. So can you account for these apparently contradictory facts with our model? Yes, we can. But I will not be able to tell you how. But in any case, the interesting thing is that I needed to introduce the interaction. And I use the Erdős-Rényi graph because I'm not an expert in random graphs. So I knew how to do the computations in this case. The under subcritical is not interesting because so I said something like critical should play the game. And I remember 1 year ago, I presented this with Eva in a meeting in Marseille, and a student asked me, Professor, do you believe the Erdős-Rényi model graph is a good model for the brain? I was a little bit ashamed because I was not aware of your paper. I said, well, I don't think so, but I was able to do the computation in this case, so now I'm proud to announce that I believe it's a very good model. Yes, the Erdős-Rényi, because I read the Siddhartha's paper with Mauro Copelli, and then Siddhartha speak about your paper, and I liked it very much, and said, wow, that's very convincing. And then Claudia here said, no, I'm not convinced because he only considered a culture of neurons. So I said, well, you tell him. She said, no, this is... But in any case, it's convincing the way he presented it. So he said, maybe he said already it. So look, I do it for the Erdős-Rényi graph, and I show a result which is compatible with the observation in Siddhartha's data and also with Goldberg and so on. So read the paper, and if you want to discuss with me, do it anytime you want. That's the end. Thank you very much.
What happens with the other 75% of the neurons in the hippocampus and with the cortical neurons?
Well, they have different trees. So a question, when you found this data, we did it as an exercise for my students. And then I said, how is it possible? These neurons are embedded in an ocean of neurons. They have been influenced by so many years. How is it possible? So maybe this has to do with the particular place or type of these neurons. That's why I ask you at that point more details about localization of the neurons.
In the cortex, it was less.
I don't remember the data of the cortex. For some reason, we start with the hippocampus because we are so obsessed by the hippocampus. We decide to start with the hippocampus.
So it's a follow-up question to that. So those, the quarter of neurons, the ones in the hippocampus, you treated them as independent neurons, not as interacting neurons.
No. I took all the neurons Siddhartha sent to me, all the neurons. I guess I had 50 neurons, something like this, and my student consider all the neurons independently.
Independently.
No. I mean, but they are not independent. They are neurons in vivo. She considers it the sequence of spike times, and ask her, please tell me what trees can you find. And then when I found these renewal trees, I was very surprised. And then I realized that Goldberg did the same observation 50 years ago for neurons in the visual cortex, I guess.
Right. But the tree is for, so you have one tree per neuron,
Yes,
not
one tree per neuron, yes.
Oh, that's what I'm saying. Okay.
Yeah. No, the problem is the following. How to make trees when you consider a system of neurons? I guess my paper is a step in this direction because we cannot represent it. So first answer, okay, you have 10 neurons, you consider the window of the 10 neurons, you have all the configuration, but this is 10 to the power 10, you cannot do it. But there is a clever way, that's the way we present it. In my next lesson next year, I give you more details. For people coming to SBNEC, I will tell them.
Just coming back to this issue, it occurs to me, perhaps naively, and after Rodrigo's lecture, that maybe those 25% neurons are the multi-unit neurons, and the others are the multi-unit neurons, the neurons in the fringe of the recording sites.
Maybe.
And this is something easily testable, and actually testable with models. It would be, if you could generate, simulate, well, you have simulated data from the core and from the fringe. If you give that to Antonio, and if he says, well, those that come from the fringe are always the ones that have this, say, lack of interactions, lack of memory, that would be, it would make sense.
No,
and it could even be a way to statistically assign multi-unit or single-unit label.
Let me make a picture. So one possible explanation for this is the following. So let's suppose Siddhartha is a very influent person. Siddhartha has a blog. And everybody reads Siddhartha's blog. And then in his blog, someday he says, look, I think the good thing to do now is to consider this problem, say, to look at the hippocampus and to see if you can find the evidence that during rapid eye movement sleep, you reverberate experience from you had during the day. So everybody looks at, wow, I was very impressed, so I wrote a project on this, and then I discussed with Guillermo. Guillermo, wow, that's a good idea. So we started doing this, and we influenced a lot of people. But then Siddhartha forgot about this. He changed his mind. He in a different mood. But one day, a blog written by Guillermo, who influenced you, and then Guillermo have a look at a blog written by Hawk, and Hawk was influenced by him. So I think we should look at the hippocampus. And Siddhartha, he forgot about his own idea 3 years ago, said, well, that's a good idea. So an information start with Siddhartha, make the entire graph and get back to him. What we are telling that this result suggests that something like this should not happen. So here you have a neuron. Here he has a spike. And then 0, 0, 0, 0, 0. And then I want to predict what's going on here. So in the model, what occurs first does not affect. But maybe this is wrong. Maybe if I have another spike here, this spike affects this neuron which affects this neuron, which affects this neuron, and then this come back as charge injected in this neuron because the entire chain. So the result says that this cannot happen. And of course, if you consider the Erdos-Renyi graph is slightly above the critical value, this is quite reasonable because you have not so many connections. The way John explained why the critical case is reasonable, he says, look, if I have a subcritical random graph, well, information disappears because it does not go very far away. You just die. If you have a supercritical, well, it arrives, but it's a mess because everybody keeps giving information. If you have a critical, slightly above, it arrives, but in a very specific and individual way. So it's wonderful. So if this is correct, the theorem we prove for this gives a perfect explanation. Just because the graph is so sparse that it takes a long time for an information to return to you. As in the case, Siddhartha's blog influenced Guillermo, who influenced me, who influenced Daniel, a long time ago it returned. So this could be, or maybe it's something entirely different. So you should look at the details of these specific neurons to find. I think it's time to go to lunch.